Neural network dynamics models for control of underactuated legged Millie robots. A small, low-cost, and highly dynamic palm-sized robotic platform that is constructed using rapid manufacturing techniques. It is 10 centimeters in length, approximately 30 grams in weight, moves up to 27 body lengths per second, and uses 2 motors to control all 6 legs. Its high speeds of operation, partially observable state space, and underactuated design combine to make the tasks of data-driven modeling and control challenging. Our model-based learning method involves using data to learn a dynamics function, and then using that dynamics function as part of a controller in order to follow desired trajectories. We implement the dynamics model as a multi-layered neural network consisting of 2 hidden layers, each of dimension 500. This function takes as input a state and an action, and outputs the state difference that occurs over the time step duration delta t. We define the state as follows. It includes the center of mass position from the motion capture system, the center of mass pose from the motion capture system, the angular velocities from the gyroscope on board the IMU, the motor crank positions coming from the magnetic encoders on the motors, the back EMF from the motors, the battery voltage, and the derivatives of some of these values. Finally, our action is defined to be the direct PWM values for the motor. Next, we discuss our controller. At each time step, we randomly generate k candidate action sequences. We then use the learned model to predict the results of executing those sequences. Then, we use a trajectory following cost function to select the optimal sequence. We execute that action, and we replan at each time step. Here, we show the data collection process. We collect training data by placing the robot in arbitrary start states and executing random actions at each time step. We collect 200 rollouts, where each rollout lasts for 5 seconds and contains 50 data points. This results in a total sample complexity of only 10,000 data points. Here, we see the controller using the learned model to execute a straight trajectory. Here, we see a visualization of that run, where the red dots represent the forward prediction of the chosen action sequence. Next, we show left, right, and zigzag trajectories. Note that the training data we use consists of only random trajectories, but at runtime, we can execute trajectories that differ substantially from anything seen in the data. This illustrates that our approach can be trained with off-policy data, and that the learned model exhibits considerable generalization. We compare our model-based method to a baseline method of differential drive steering. Here, we show plots of cost versus speed for 2 different types of trajectories. Our experiments showed that the baseline is comparable to our model-based method at low speeds. However, as the lower green line shows, our model-based approach outperforms the differential drive strategy at higher speeds, where traction decreases and the contact dynamics change. Improved performance of our model-based learning approach with more training data. Here, we show a trajectory executed by models that were trained with different amounts of training data. We see that the model trained with more data on the left performs better. We conducted a study with 3 different models, and as seen by the average trajectory following costs in this table, more training data can indeed increase task performance. This is an encouraging indication that improvement can occur over time, which is not the case for hand-engineered solutions. Different surfaces. We conducted experiments using our model-based learning approach on a carpet material, as well as a styrofoam material which was slippery and had no compliance. As seen from our experiments, the model trained using data from carpet works well on the carpet, and the model trained using data from styrofoam works well on the styrofoam. The poor performance of either model on the other surface suggests that our learned model does in fact encode some environmental information about the surface.